Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Senyola and I'll be walking you through the physics course. Today we want to consider reflection of light waves. We will consider it under the following subheadings, that is, the nature and source of light, transmission of light, rectilinear propagation of light, reflection of light from plane surfaces, reflection of light by curved mirrors, formation of images, and finally the use of convex driving mirrors. Okay, let's start. What is light? That actually sounds like a very interesting question. Everybody knows what light is. Light is that thing that brings about illumination and allows us to see, right? Well, light is a form of energy that supports and assists seeing. It is a form of energy that supports and assists seeing. It supports the act of vision, it supports the eye in the processing of information. So, when we talk about light, what are the sources of light? We have very many sources of light, especially in our time. But the ultimate source of light is the sun. Our light also can be generated from heat, can be generated from fire, of course. Our light can also be generated from electricity, that's our electric bulbs, can be generated from different sources. We've spoken about the nature of light and some of the sources of light. Some questions will pop up on your screen. Please answer them. I want to see how well you understand the topic that has been taught so far. Come back. So, we've talked about the nature of light and the sources of light. What do we mean by transmission of light? Transmission of light simply has to do with us taking light from one particular location to another particular place where it is required. There are three types of transmission that light may go through. That is, our light rays can be seen in three types of ways. These are the divergent beam. In the divergent beam, a speck or a tiny source sends out light and sends it scattered. So the light is coming from one point and is going out scattered like that, just like we have it from most of our lights, our flashlights, our lamps, the car headlights. They are most of our appliances are divergent light. They want the light to spread. The light goes out and it spreads. Also, we have what is known as the convergent beam. The convergent beam is the exact opposite of the divergent beam. In the convergent beam, instead of the lights scattering abroad, the light is gathered to one point. Instead of the lights scattering abroad, the light is gathered to one point. The knowledge of this also finds its use in many things, such as in the operation of heavy machinery, like and harmful. Actually, they can be harmful, like our reactors, our radiation controllers. Also, in the medical lines, when we find the use of gamma ray and X-ray in cutting off of cancerous cells and treatment of other ailments. We have the third one, which is known as the parallel beam. The parallel beam. In the parallel beam, each line of light moves, not converging, not diverging, just moves in his or our own line. So these are the three types of beams we have: the divergent beam, the convergent beam, and the parallel beam. Let's talk about rectilinear propagation of light. Rectilinear propagation of light. The concept of rectilinear propagation of light simply talks about the fact that light can only move in a linear direction, that is, can move in one direction, and light does not possess the power to bend. Light does not have the power to bend. When the light source is shining on someone, and maybe we have a light source like my candle, and the light is shining, and it happens that there is something in the path of the light, we'll notice that there will be something called a shadow. There will be something called a shadow, and there will also be something called an image. The shadow, actually, it is an evidence that light does not have the power to bend. If light had the power to bend, the light would have just simply moved around the object and continued on its path, leaving the entire situation without shadow, leaving the entire system without a shadow. But because of the fact that light possesses a rectilinear property, it can only move in its own direction. It cannot bend. It has to pass through and leave a shadow behind. Other experiences, other situations that have proved this particular phenomenon, that's the rectilinear state of light, includes the eclipse, that is eclipse of the sun, eclipse of the moon, where actually things stood in the path of light, and instead of light to bend and find its way to us, it refused to. Why? Because it just couldn't do it. Okay, let's also look at the benefits of this particular feature of light. Do you know that the idea of the camera came from the understanding of the rectilinear propagation of light? The camera simply it contains a lens which actually either magnifies or reduces the size of a thing. So sometimes we have magnifying lenses, sometimes we have converging lenses, we have reducing lenses. So each of these things, all these things, the rectilinear properties of light was what was put into consideration, what was put into active use to design all these optical devices. Another thing, of course, that's one of the principles that was understood, that one of the things we were able to draw out from the understanding of rectilinear propagation of light is the magnification of objects or images. How does this work? When we talk about magnification, what is magnification? Magnification is simply in in physics, that is under the topic of light in physics, magnification talks about the rates. Magnification talks about the rate of the image in relation to that of the object. That is, magnification represented by m can be calculated by height of the image divided by height of the object. It can also be calculated by the distance between the image and the lens, that is distance of image, and the distance of the object. So that's how we calculate magnification. Now, if you're considering distance of image and distance of object, distance of image is restricted to how big the camera is. So you can also call it length of the camera, that is the length of the lens, how far the length of the camera is from the back of the camera compared to the distance between the camera and the person that is being snapped. Alright, that's about all on magnification. Let's talk about reflection of light from plane surfaces. Reflection of light from plane surfaces. And this subtopic, the most important thing we need to bear in mind is the reflection laws. The laws of reflection. The laws of reflection. The first thing we need to learn to understand is the principle of the mirror. When you take a mirror and you stand in front of the mirror, you see yourself. So how does this device called mirror, how does it work? Alright. On the mirror, let's take this as a smooth mirror. A particular light is being shone on the mirror. The lights will be reflected by the mirror. This is the shaded part of the mirror, or the back of the mirror. The light will be reflected back by the mirror. This is incoming and this is outgoing. Now this one that is incoming is known as the incident light or incident ray, while this one going away is known as reflected ray. The one coming in is known as the incident ray, while the one going away is known as the reflected ray. Now there is an imaginary boundary that exists, kind of like a border. That border is perpendicular to the surface of the mirror. Perpendicular to the surface of the mirror. And it usually finds its way in between the incident ray and the reflected ray. Now, there are things to note, and these are angles. The angle of incidence is known as I, angle of incidence. What is angle of incidence? That is the angle that the incident ray makes with the normal, to the mirror. This perpendicular line is known as the normal. That's the normal to the mirror. So, incident ray is the incident angle. Incident angle is the angle the incident ray makes with the normal, while R is reflected angle or reflective angle. The reflective angle is the angle which the reflected ray makes with the normal. That's the first thing that the law of reflection talks about, that there is a normal in between the incident and the reflected. Now, the second thing it states is that the angle of incidence equals the angle of reflection. Angle of incidence, I, equals to angle of reflection, R. So, this finds a lot of use when we're doing most of our calculation. What if in a particular situation I have a particular mirror set at a particular angle and I decide to tilt the mirror because I want to achieve a purpose? What would happen? What would happen when a mirror originally staying like this, and I have had this is my incident ray, this is my angle of incidence, and I already have my R as well, and then I decide to tilt the mirror to something like this. Now the mirror will develop a new normal. That's the first thing that will happen. And that new normal would be let's take it as that. I'm using dotted lines to show the new appearance. Now, the angle of incidence, if you look at it, is now narrower. It's now something like this. So my angle of reflection too will be narrower, because angle of reflection is always equal to angle of incidence. So, sorry, this should be R. I2, I1, R1. So, that is one of the things that do happen. If you make an observation, the change is very radical. So, mathematically, to express what level of change would have happened when you adjust your mirror by the angle of theta, the effect on the system would be 2 theta. Why? Because half of it will go to the angle of incidence, the other half of the effect will be experienced by the angle of reflection. Before we leave this topic, what about in situations of more than one mirror being in use at a time? Maybe we have 2 mirrors, a situation of 2 mirrors being put together and being looked at. We want to know how many images would be displayed on the screen. To calculate that, number of images would be equal to 360 divided by theta, minus 1. 360 divided by theta minus 1. So, while theta is the angle between the 2 mirrors. So, if I should get 2 mirrors and I should put them at 60 degrees to each other, my answer will be 5. So when an angle of 60 degrees is between 2 mirrors, you have 5 images. If you happen to have the like what you express in the barbing salon, you have 2 mirrors and there is no angle between them, that is, the angle between them equals 0. In that kind of condition, you have from the formula, number of images would be equal to 360 degrees divided by, since there is no angle between those mirrors, they call 0, thus they are parallel to each other, minus 1. Now anything divided by 0 equals infinity, minus 1. So you have infinity number of images. And that's why when you look into a mirror in the barbing salon, you see yourself, you see the mirror, you see the image of your image, and the image continue replicating like that. You keep seeing that inside the same mirror until there is almost no space for you to look and see inside the mirror or in of one of the mirrors. So that's let's consider reflection of light in curved mirrors. When we talk about curved mirrors, what do we mean? To develop a curved mirror, we get a spherical glass. A spherical glass that has a hole or an hollow in the middle. For example, the process that you can use, you make a mold, kind of a mold, and then you pour liquid glass into the mold. Maybe the mold will be made of a spherical shape, and you pour the liquid glass into it, allow it to cool, and then you have your spherical glass. Now, for the spherical glass to be usable, to be convertible into a mirror, you have to coat it with silver or a silver colored material. When you want to coat it, there are 2 directions in which it can be coated. Since it is semicircular, sort of, it is spherical, but the shape, when you look at it, it looks like a semicircle. So it can be coated inside and it can be coated outside. It can be coated inside and can be coated outside. When you coat it outside, a concave mirror is formed. A concave mirror is formed. So, well, the concept of before we go further into it, let's consider the concept of concave and convex mirrors. Though a little difference occurs between them, and when we consider the mirrors and lenses. When we're talking about a convex lens has a shape something like this. Now, the concept of a convex lens is that the lens gathers light towards a point. It gathers light towards a point. So the convex lens has the power of converging light. Convex lens has the power to converge light. So when light is coming, parallel light or parallel beam, when it comes in contact with the convex lens, the light begins to come together, and then they come to a point. They come to a point. That's what happens inside the convex lens. Now in the concave lens, it has divergent properties. If the same light, the same rays of light approach it, when the light hits the surface, it scatters. So say the light is divergent, just like we explained earlier when we were talking about the 3 types of light transmission. We have the concave beam, we have the convex beam, and we also have the parallel beam. Now, basically, to identify them, the concave lens is like two different lenses that are turning their backs on themselves. It's like 2 curves with their backs towards themselves. That's why it's called concave. It is just as we have it here. They are having their backs towards themselves. In the convex, they are like gathering themselves together. So it's like, let us converge already, just as the nature of the beam that comes out of them already talk about. Now, it is easier to work with the lens because the lens actually make more sense when you think about the concave and the convex thing compared to when we get to mirrors. Because the concave lens is a converging lens, which is it is bringing it together. Of course, the convex lens rather is a converging lens. It brings the light together, while the concave lens, because of the nature of this thing, it shares the light abroad, where the curves do not have an agreement. You can look at it you can picture it from that perspective. In the convex lens, there is an agreement between them, so they are able to bring the thing to the center point. That's to your eye sight. That is where your blind spot in your eye. That's the location where your light, the image of anything you're looking at, is supposed to fall for you to see. But the convex lens, it scatters it. Because they are not in agreement. The concave lens, it scatters it because they are not in agreement. So it sheds the light further. Before I continue to talking about the mirrors, in your eye, the process of your eye, the process in which we do see, it involves this concepts. That is, the human eye has the lens somewhere there, and the location of the blind spot. I know you do this more in biology, where they will be trying to, and you definitely have done something like this in your basic science. Retina. Okay. No, the retina is a thing. The blind spot is a spot on the retina. Yeah. The blind spot is where the light falls on. So when the beam of light coming from outside touches the surface of the lens, the convex lens inside the eye pulls the lights together so that the image of the light falls on the blind spot. If it does not fall on the blind spot, the person would either not see or not see clearly. In the case of people who have myopia, that is short-sightedness, people who are short-sighted, the image is falling at the back of the blind spot. So they need something to scatter the light the more. That's why they are given, the image is falling at the back of the blind spot. So they need something to bring the light together earlier so that it can fall on the blind spots. Myopic patients have something like a convex lens will be introduced to the system so that it is already bringing the light together. And since it's already bringing the light together, the light just falls easily on the blind spots. While as in the case of those who are far-sighted, the image fall is created before the blind spots. The image is created before the blind spot. So they need the light that is coming into the eye to spread out a little more, so that by the time the eye lens is gathering the light together, it will fall on the blind spot. That's why the use of concave lens is adopted for them. And in this case, let's say this light is coming, the light enters this way, and it scatters more. So the light that comes out of it is converged into the blind spots. So that's one of the applications, one of the use of lenses. They are used in making glasses, they are used for magnifying objects. But the difference between the lenses and the mirrors, in a concave mirror, in a concave lens, the lens scatters the light just the same way a concave lens is made. I'm sorry, this is convex lens. Concave lens, instead of it scattering the light, it brings the light together. It brings the light to one spot. So when the light is coming, it reflects the light and brings the light to one spot. There are some terminologies that we need to keep at heart, especially when we're working on lenses and mirrors. Terminologies as the focal length, the radius of curvature, also image distance, object distance. These are terminologies that we do use in our calculations having to do with light, that's reflection, either mirrors or lenses. We'll also be talking about magnification, because that's basically what all these things do. So it brings in the light to one spot. So where our convex lens, concave lens, where our convex lens is a converging, has a converging power, our concave lens has a diverging power. Our convex lens has a converging power, our concave lens has a diverging power. And in like manner, our concave mirror has a converging power. That's the confusion. That's where the confusion usually come up. But just bear it in mind that whatever kind of power your lens has, the mirror has the exact opposite kind of power. So convex lens is converging, concave lens is diverging, and as such, convex mirror is diverging and concave mirror is converging. Now, what do we mean when we say radius of curvature? The radius of curvature. The radius of curvature is the radius of the sphere from which the lens, the mirror rather, is being cut out of. That is, the sphere that we're about to turn into a mirror. Of course, originally it has a radius. So that radius R is known as the radius of curvature. And it is very important because R equals to 2F, where our F is the focal length. The focal length. The focal length is the point where all the light would eventually converge to, or where all the light converges to. So in a convex mirror, as the light comes, the light converges to the focal point. So focal length is from the mirrors to the place it would have converged to. It cannot converge there because the mirror would reflect back out the light. That's the first thing. And aside the fact that it will reflect back the light, of course, it also shows the path through which the light will be reflected. So we know that our convex mirror is a divergent mirror. A divergent mirror. So the light would come out like this. That's why our convex mirrors are used for making shaving mirrors. No, they're the ones used don't worry, cut that part out. Cut that part out. I'm telling him so he will not cut out the part of what they are used for. We'll talk about that later. So it spreads the light across. In same manner, when we are considering our concave mirror, the concave mirror reflects the light in this direction. Of course, nothing can be formed at the back of the mirror. Nothing can come up there. So it reflects the light back to a point. Now this particular location is our focal point. So the distance between here and the surface of the mirror is our focal length. Now we have to talk about virtual images and real images. Virtual images and real images. Virtual images are images that are apparent. They cannot possibly be real. The way when we are looking at them, it will look like something is behind the mirror. The image is not formed on the mirror. That is what we experience when we are looking. That's what happens when we are looking at our convex mirrors. The images they form are apparent. They look like they are at the back of the mirror. But in our concave mirrors, the images are real. Because when the light is reflected back, we can actually look at the image itself. So, when you're looking at something from the focal point, the vision is super clear. It's very clear. As against when you're looking at things before or after the focal point. This is one of the reasons why when we want to use a projector, you see that the person who is operating the projector tries to adjust and adjust until the thing is clear. Also the same thing in our cameras. If you go back to those days when we use our conventional camera, those ones that we have to adjust the lenses manually. That doesn't have autofocus. You have to adjust and adjust the lens. That's moving the lens forward and backward until you are having a good focus. Now, what they are trying to do is they are trying to adjust the position of the lens such that the light would the focal point would fall on the location where the lens is. The lens should be in the place where it can take a clear picture. Of course, working with the focal point. That's where the clear pictures can be taken. Well, when it comes to questions, the formula to ultimately note is that 1 over image distance plus 1 over object distance. U is our object distance while our image distance is V. So 1 over object distance plus 1 over image distance should give you 1 over the focal point. And this is applicable to the concave mirror. It's applicable to the convex lens and applicable to the concave mirror. This is because the light is converging. When it comes to our calculations under mirrors, under lights, that's conversion, reflection, we have the formula as is 1 over U. Our U is our image distance plus 1 over V, where our V is our U is our object distance, while our V is our image distance, will be equal to 1 over focal points. This applies for, let's figure out whether it is converging light or diverging light. If we multiply the entire expression by V, we'll have 1 over U plus 1 over V equals to 1 over F. Multiplying the whole expression by V, we'll have V over U plus 1 over V equals to V over F. And dividing the whole expression by V again, we'll have something like, this is V over V which is 1. V over V will give us 1. So if we look at this, from what I told us earlier, M, which is magnification, equals to image distance divided by object distance. So M plus 1 equals to V over F. This applies to M plus. When we have plus 1, it applies to diverging mirrors, or diverging lenses or mirrors. Diverging. Why? Because the image is getting, the magnification is bigger. It is an expansion magnification. So it suggests that this is applicable to the convex mirrors. Is applicable to the convex mirrors. So for the ones that bring the lights together, that's the converging mirror, the expression will be 1 over U minus 1 over V equals to 1 over F. So this one will be applicable to the concave mirrors. Let's also bear in mind, I said earlier, our F equals to R over 2, where our R is the radius of curvature. Our F equals R divided by 2. So if you are just given the radius of curvature of the mirror, you can as well go talking about reflection of light by curved mirrors, and kind of carried along the formation of images while doing that. So what's the use of convex lens as driving mirrors? That's in driving mirrors. The other time I was explaining how convex lenses, convex mirrors, that's the silver coating is on the inside of the mirror, so the reflection is outside, and when your light shines, it scatters abroad. So basically, it's kind of allows things that are far. It helps our line of sight to see things over a wider region. That's why if you look at a driving mirror, you notice that it is written there, these objects are not as far as they appear to be. They usually engrave it on our driving mirror. This is to alert the person driving that it may look like this thing is almost touching you, but there is some gap. The reason why it is able to do that is because it accommodates more images. The images of a convex mirror are not real. They are virtual and they are enlarged. The magnification is always positive and the focal length is negative, because the image is not formed in the direction of the focal length. The image is formed in the opposite direction of the focal length. In this lesson, we considered reflections of light waves, and we spoke of the nature and sources of light. We spoke of the transmission of light as well, that is, light moves either in convergent rays, parallel rays, or divergent rays. We talked about the rectilinear propagation of light, which suggests that light cannot bend, it moves in straight lines. We talked about the reflection of light from plane surfaces, that is, straight mirrors. We looked at the number of images that will be created when two mirrors are placed side by side at angles between them. We also talked about reflection of light by curved mirrors, where we started working with the formula that we gave earlier. 1 over U, which is object distance, plus or minus, depending on the situation, 1 over V equals to 1 over F. We talked, that's also part of image formation. Image formed by a concave mirror, that's a diverging mirror. It is real, it is inverted. The images formed by a concave mirror is real and it is inverted. But images formed by the convex mirrors are unreal and they are erect. They are unreal and they are erect. The image formed by the concave mirror is real, it is inverted, and of course at the same time it is enlarged. Erect, they are virtual and they are diminished. That is, it compresses the environment. It makes things bigger look smaller, like we have in our roadside mirrors. That's the mirrors placed on in corners of the road, so that as to show a larger area. Also, we see it in our stores. We have our convex mirrors strategically placed so that the store owner can keep watch of events happening everywhere in the store. I haven't spoken about this interesting topic. Some questions will pop up on your screen. Please do well by attempting them. And if there is anything along the line which you do not understand, you may view the video one more time.